In exercise 3, we have two integers a and b, and we wish to prove that a minus b is a factor of a to the n minus b to the n when n is a positive integer. And this is something we'd looked at in a previous proof. We used it in the previous proof to help us prove what we were looking for. And now we're actually going to prove this theorem itself. This is a consequence of the factor theorem, but we're actually going to use it. We're actually going to prove it using mathematical induction. So our proposition, of course, is that a minus b is a factor of a to the n minus b to the n, where a and b are integers, and n is a member of the integers with a little plus sign. What's that mean? That means n is a positive integer. And so z, like this double-stroked z, stands for the integers, and when you add a little plus subscript to that, that means the positive integers. And so that's what we're saying here. So let's look at the first step. We want to show that this is true when n is 1. Well, trivially it is, because a minus b is a factor of itself, and so that's pretty easy to do. Step 2, we want to assume that a minus b is a factor of a to the k minus b to the k. And so we need to write that in a way that we can use it. And again, that's what we've done here, right? A to the k minus b to the k is equal to q times the quantity a minus b, where q is some expression in a and b. I don't know what it is. I don't need to know what it is. Q is an integer because a and b are integers. But if a and b were not integers, if a and b were more variables or something, then q correspondingly would be of a different type. So we're assuming this equation is true. Now we're going to take that assumption and show that if it's true, then a minus b is also a factor of a to the k plus 1 minus b to the k plus 1. And again, expressing that is a matter of defining a new variable I'm calling r, which is an integer, and saying that r multiplies the expression a minus b. And again, notice the question mark over the equal sign. I'm not asserting this is true. I'm trying to prove that it's true through algebra. Your goal in mathematical induction on that third step is almost always to look for a way to incorporate your assumption step into the step that you're proving in some way that allows you to do a substitution. And so that's what we're going to do right now. I'd like to find a to the k minus b to the k somewhere. And obviously we can't use what we're trying to prove. That's another mistake that I see commonly. People use the very thing you're trying to prove in the middle of your proof. Well, no, I can't use that. That's what I'm trying to prove. So we need to go about it some other way. And this one's actually very tricky. A little bit of a clever way of using algebra to do this. And so it's not obvious, but I'll show it to you. This is just another example of an interesting proof to kind of get you used to what proofs look like and being able to write them well yourself. So what we do here, that's the trick, is to subtract and add the same quantity on the same side of the equation here. So on the left side, again, I'm only working on one side, so what I'm doing is perfectly legal. I'm going to subtract a to the k times b and add it right back, a to the k times b. So I've added nothing, but I've added nothing in a form that's going to actually enable me to factor things in a way that shows me that what I'm trying to show is true. So we've got a to the k plus 1 minus a to the k times b plus a to the k times b minus b to the k plus 1. And I'm hoping that that equals r times the quantity a minus b. Well, looking at the first two terms, I'm going to factor out an a to the k from those first two terms, and I see, lo and behold, an a minus b factor. Perfect. That's helpful because I want this whole expression on the left side to be factorable by a minus b. I've got two terms. One of them I already know now is a factor of a minus b. If the other one also has a factor of a minus b, then I'm all set. So from the second two terms, I'm going to factor out a single b, and I'll have a to the k minus b to the k. Well, what's great about that? What's great about that is this is the expression from my assumption step. So again, we're looking to find my assumption expression in the expression I'm trying to prove so that I can do a substitution. And so I've got an a to the k minus b to the k, which I've assumed equals q times the quantity a minus b. And so I'm going to do that substitution. Now we've got two terms, each of which has a factor of a minus b. which I can factor out of those two terms and see that yes, indeed, the left-hand side is divisible by a minus b. The multiple that it leaves, the other factor, is a to the k plus b times q, which is what our r happens to be in this case. And so we found a way to show that the left-hand side is divisible by a minus b. Therefore, a minus b is a factor of a to the n minus b to the n for all n in the natural numbers and the positive integers, natural numbers, same set. You'll notice here QED at the end of my proof. That's abbreviated for the Latin quod erat demonstrandum, which means roughly that which was to be demonstrated. And so you'll often see proofs in textbooks and things ended with QED just to denote that the proof is finished.